Structuring Systems, an application of basic structural modeling. This is the third video in this series. It's part 2. We have an introduction, which orients the viewer to the project, where the materials are located. This is my website. It has a lot of supporting material on the website that's associated with this basic structural modeling project. It's my Twitter feed where I make announcements of new videos. You can ask questions, send messages there, and so forth. So the basic structural modeling project overview, I'm going to go through the introduction, not in as much detail as I did last time. I've added some material to the fundamental concepts, and then we'll talk a little bit more in depth about the ordering process. We're in the conceptual solution phase of this project, and the ordering process is something that we're going to have to implement in code. So we need to look at this, talk about it a little bit, and come up with some ideas and fundamental requirements for the process in the software. Process steps, process summary, and conclusions. Probably won't go through those in much detail in this video, but in later videos. So in this particular case and the problem that we're working on here, we're working with 19 cities in unknown, unordered state. So we define a system as a relationship mapped over a set of objects. The 19 cities are the objects. The is north of is the relationship. And we want to order those so that we have a known ordered state. And we do that by collecting empirical data. But collecting empirical data costs money. So we use some inference and other techniques to reduce the cost. We'll go through these particular detailed steps in later videos, how that inference and the integration works. But what we do is essentially we just collect 25 data points at random, then we order the cities, then once they're ordered we do some inference and we collect more data and so forth until all the cities basically are ordered. Our fundamental concepts that support the abstract relation type and this type of basic structural modeling includes the utilization of the 3 fundamental types of truth. There's formal truth, factual truth, and value truth. And the authors have created an abstract relation type, which is an approach that allows us to use all of these types of truth in the same type of computational system. Formal truth, factual truth, and value truth have had kind of 2 different kinds of computational systems, with formal truth and Prolog and different types of logical operators are a little bit different than the arithmetic and mathematical operators that are used in factual and value truth data manipulation and data analysis. So we create an approach that allows us to use all those together, and this is basically founded on the work that was done by John N. Warfield in systems science. So our abstract relation type integrates these truth operations. The marking space supports formal and factual truth. Value space supports value truth. And of course, we'll look at the system structure and the components. Those are important parts. So here's a definition of 3 types of truth. If you're having difficulty reading these slides, the website that I pointed to, or where you got the links to the video, has an accompanying set of charts for each video part, so you can download those charts and read the information right off the charts. So formal truth really depends only on the logical connectivities in the sentence. Factual truth depends on the state of the real world. And value truth is determined in a number of different ways, and it really expands to ethics, culture, prediction. But it's also technical expertise, professional expertise. There's a lot of different ways that we deal with value truth, and it's a very important part of systems and system science and systems engineering. And in our activity here, we'll be using value truth and actually the value space to help us in the computational side. So it'll be a little bit interesting approach. We call it that value space application. We call it a system number. It's something that the authors have developed to help us in these computations. So here's the types of truth: formal, factual, and value. The examples, of course, in the formal truth is A is B, A is not B. If A, then B. These are formal logical types of statements. Factual truth is John is a man, John is not a man. And value truth, of course, is John is a good man, and John values gold. So that essentially these are statements about the world, but they are in completely different forms, but they all contain a type of truth, and we're going to use all of these. And here, are they known by experience? Well, formal truth is not known by experience, where factual truth is, and in value truth, sometimes yes, sometimes no. So we, in engineering and system science, we're really interested in applying our techniques to the real world, and we get feedback through experience. So we're very interested in using formal truth to help us achieve these goals that are really necessarily delivered using factual and value truth. So the abstract relation type is just a notional type of explanation and overview of an abstract relation type. An abstract relation type has three components: as a marking space, an outcome space, and a value space. And marking spaces can really have one or more sections. Outcome space can have one or more sections. Of course, here we depict the value space with more than one section. And each section of these spaces can have one or more matrices. So what we do is we use this as an organizational scheme to allow us to use the different types of mathematics that have been developed for different types of truth processes and different types of problem-solving areas. So abstract relation type has three main parts. It has a prose description of words. You can have a formal pattern. It can have an informal pattern. But you need to have a textual description, a fairly formal description of what this specific art does. It needs a graphic representation. It needs directed graphs. That's formal graphs. It can also have informal graphs. And then mathematics and computer representation. You have math equations, computer code, one or both. So really what we have is an abstract relation type. We create an equivalency between these forms. So really, fundamentally, we have a model exchange isomorphism, which was developed by Warfield, which we can then have a specific exact representation of a set of prose in graphics and have a set of prose in mathematics. We can convert between these different model representations. So this allows us to quickly communicate with people that don't understand mathematics. They can use prose, or we can show them a graph. But the model exchange isomorphism assures us that we are communicating the same type of information in any form. And in the graphics and mathematics and systems engineering, and in engineering particularly, are mostly focused on graphics that are used for design. They use a design type of graphics representation to show the design to the people that are going to actually need to understand it, approve it, build it, so forth. But one of the primary ideas, again, that the authors have come up with is we really use systems idea, and we use the systems concepts in two different modes. We use it in the design mode, and we use it in the discovery mode. And in the design mode, you know the relationships, and you're designing the objects. In the discovery mode, you know the objects and you are discovering the relationships. In this particular case, we know the objects, we know the cities, and we're going to discover the relationships between each of these particular city pairs. So the types of mathematics and graphics that we're going to use here is not the same as like UML or SysML or IDEF0 or any of those other types of graphic modes that you would use in the design mode to actually document and capture your design and communicate your design. So the graphics we're going to use are going to be down here in the discovery mode area, and they will allow us to do things in a little bit different way than we would use graphics in the design mode. So the system structure components. A system is a relationship mapped over a set of objects. We know the cities. We know the general relationships. So the cities are the objects, the general relationships north of. We must discover the specific relationship between each city pair. Okay, the ordering process. This is a list of the types of activities that we'll go through to complete the ordering. You can click on any of these to take you to those parts so that you can see where they are. We'll skip that at this time and go right to the beginning configuration. Again, if remember from the other videos, we have 19 cities in the beginning. And we put them on a self-interaction matrix. We have no information about their ordering, none. So we place zeros in the matrix in all the cells, and we also then use coloring background to make a determination of actually what the zero means. So a zero with a yellow background means it's unknown. We really have no information about this interaction. And a zero in a red background means that's false. So we have no information, so how do we know that this red is false? So let's read what this matrix says. What does this matrix say in prose, in English? What it says is city 1 is north of city 1. It says city 2 is north of city 2. That's what these red zeros on the diagonal mean. And so from logic, from formal logic, and from a natural language relationship, we will not allow a city to be north of itself. So we give that a red background. We know from logic and we know from formal logic that a city cannot be north of itself. City 1 is north of city 1. No, that's false. City 2 is north of city 1. Well, it's unknown. We really don't know yet. We have no information about these. So then we go through and we collect the empirical data. Just 25 cities at random, and you can see this is just a random scatter plot of data that we acquired about these cities and their relationships. So what does this say? City 2 is north of city 1. Yes, that's green. That green 1 means yes, that's true. But then we know that if city 2 is north of city 1, then city 1 cannot be north of city 2. So we infer a red 0 here. These pair together. And you can see this pairing in here with city 5 and city 1, city 1 and city 5. Is city 1 north of city 5? Yes, that's true. Is city 5 north of city 1? No, that's false. So in this process, what we know at the end, we want to have all the green ones down in this lower triangular and all the red zeros up in the upper triangular. That is going to be the situation or the final process that we're looking for. So we need to start swapping rows and columns to start moving the green ones into the lower triangular. That's the ordering process. And that's kind of the area we're going to emphasize in this video. So here we swap column 5, row 14. So row 14, here's row 14. Yep, And then there's 5. So here's where 5 and 14 have been swapped, and 14 and 5 have been swapped. So this green one that was up here, let's look and see if there was a green. So 5, yes. So 14 and 5, there was a green one there, right there. It has now been moved down. See, now we have a red 0. So in swapping those rows and columns, what happens then is we change the configuration of the system. And then we change the system configuration to bring the ones into the lower triangular. And then we swap column 14 and 11. And then we swap 4 and 10. Then we swap column 1 and 2 up here at the top, okay? Swap column 1 and 2, we brought the 1 into lower triangular up here, put the 0 up there. And then we swapped column 2 and 11. So now what we're doing is we're starting to, instead of randomly just selecting cities that were in the upper triangular, we're starting to have a strategy about how to actually solve this problem. If we think about this, what we know that when this is all done, when the system is correctly ordered, that there will be zeros. The top row will be zeros. So we know then, and as we have here 11, right? This is zeros all the way across. And then we will find the next row that has zeros. Here's one that has zeros. So which one is the candidate for up there? This one, or here's another one, 13 down here, all zeros. So that is a way that we may want to go through and think about which pairs of cities we should look at next. In this particular case, we have been swapping the rows and columns and working our way down. So we're working our way down. The next ones here look like to be like 10. Let's see, the city 10. Is that next? Yes, 10 and 1. So we start swapping these so that we're able to move more of the green ones into lower triangular. And then we're doing 10 and 6. So then we'll do 6 and 14. So again, working our way down. So up here, there's no greens in this upper triangular portion up here. And we're going down this way, looking for the next greens and swapping those out. Okay, so that was 14 and 17. So what's the next ones here? What, it looks like 6 and 10. See what that says. Well, or 10 and 14. Okay. And then, as you can see, we're moving our way down. No green ones at all up here. Now, this one down here, of course, is what, 10 and 4. That's it. 10 and 4 has been moved. And now we've moved all of the green ones that we have. We moved those down into the lower triangular. We still have a number of rows that have no ones in them. So when we go collect information, these are candidates for collecting information, but we're not doing directed information collection yet. We're just still doing random information collection. Okay, so we then, before we collected the information, we did the inference on this set. Took this set, we did the matrix inference operation with the reachability matrix. That operation we will go through in more detail in the next video. Start wrapping this up. So the blue ones here, of course, come from the inference, and then the additional greens, we got these from collecting new information. And then we'll go through and order this. You can see how we move all the things from the upper triangular to the lower, all the ones, move them. We got one more down here, right down here in the bottom, move those over, and then we're done. So then we iteratively go through and do this process. So in summary, what we've done is we take an unordered system. We take that unordered system, we order it collecting empirical data. We get efficiencies from and maximize the use of our empirical data by using inference techniques. And those inference techniques are a direct cost reduction process. And we'll go next week into the more detailed steps in the inference process, and that will be part 3 of this particular video series.